Okay, let's unpack this. We have a really fascinating stack of sources that they challenge us to look at the universe's ultimate structure.
They really do. I mean, it's the biggest question, isn't it?
Are things infinitely divisible, or do they just stop at some fundamental particle?
And is reality a continuous dynamic field? Or is it made of countless discrete little building blocks, like monads or something else?
That tension, discrete blocks versus a continuous flow, it feels like the deepest philosophical puzzle underpinning all of science.
It is. So our mission today is to trace this millennia-old conflict. We want to show you how these ancient arguments about the nature of matter are still powering the most cutting-edge physics theories in the 21st century.
And the goal for you listening is to quickly grasp these core, often opposing viewpoints on matter and reality. And maybe to realize that the difference between, say, Democritus's atom and a modern quark might be smaller than you think.
Great place to start. Let's go right there, 5th century BC, atomism. This was just a brilliant attempt to reconcile change and stasis. Leucippus and Democritus, they basically posited that if you kept dividing matter forever, you'd run into a serious philosophical problem.
So their solution was that it has to stop somewhere.
It has to stop at a tiny, solid, indivisible unit, the atom.
And the space between them was just as important, wasn't it? The existence of the atom required the existence of the void.
Absolutely. The whole idea was that the world we observe, the world of motion, growth, decay, is simply the arrangement and rearrangement of these static, indivisible atoms moving through empty space.
It's an explanation for change without the underlying reality itself having to change.
Precisely.
But not everyone was happy with just hard, featureless spheres. Plato, for instance, he introduced geometry into the mix.
Yes, which allowed for a much more flexible view of these elemental building blocks. Plato assigned specific geometric forms to the elements, drawing on the perfect Platonic solid.
So like a cube for Earth because it's stable.
Exactly. Earth was the stable cube, while fire was the sharp, mobile tetrahedron. And the key insight was that these fundamental bodies could be broken down into basic triangles and then reassembled.
Which explains how one substance could change into another.
Huge step. It was a huge step in accounting for the complexity of chemistry.
But this philosophical idea of the atom then sort of went into exile during the Middle Ages. Scholastic thought was more focused on Aristotle's ideas.
On the minima naturalia, yes, the smallest natural portions of the substance. And it really stayed in exile until the 19th century, when science finally caught up through empirical observation.
John Dalton's moment.
That's the one. He observed that purified substances always broke down into the same elements in the exact same fixed proportions by weight. That observation made the conflict of fundamental particles, atoms, a necessary scientific reality.
Okay, so that brings us to the dawn of classical mechanics and that epic 17th century battle between particles and fields, spearheaded by two giants, Isaac Newton and Gottfried Wilhelm Leibniz.
This is where the tension becomes, quantifiable. Newton gave us the bedrock of classical mechanics. He invented calculus and gave us the first real quantitative analysis of gravity.
Realizing it extended all the way to the moon.
In a precise inverse square proportion, 1/r².
We often think of Newton as the particle guy, all hard billiard ball dynamics. But even he wrestled with the continuous nature of light.
Oh, he certainly did. In his optics, he described light as having both corpuscle-like properties, tiny particles, and wave-like properties. He literally described the foundational quantum paradox centuries before anyone else.
He knew light had to be both discrete and continuous somehow.
Exactly. Now, if Newton was the king of the discrete, then Leibniz was the champion of the continuous and the relative. He proposed a universe built not of atoms, but of monads.
And monads are fascinating because they're not really physical objects in the same way.
Not at all. They're simple, unparted substances that are centers of force and perception. They have no physical extensions. They're essentially these infinitely complex points of view.
So they aren't physical parts, they are more like informational substance.
Precisely. And this is why Leibniz argued so fiercely against Newton's idea of absolute space and time. For Leibniz, space and time were entirely relative.
Just the order of things.
Just the order in which coexisting or succeeding monads express themselves. I mean, this worldview is so foundational that Albert Einstein later called himself a Leibnizian.
And Leibniz even built this idea of continuous self-referential structure into mathematics itself.
Yes, his ideas on self-similarity and the principle of continuity, natura non facit saltus, nature makes no sudden leaps. That laid the philosophical groundwork for what would become fractal geometry.
Okay, so speaking of discrete discrete particles trying to explain continuous forces, we have to talk about Lesage's theory of gravitation.
A great historical example. Lesage's theory from the mid-18th century was a purely mechanical attempt to explain gravity. He imagined the universe was filled with tiny, ultra-fast-moving particles.
Gravific particles, he called them.
Right, and they're streaming randomly, pushing on all objects. So gravity is just the result of one object shadowing another, creating an unequal pressure.
It sounds so simple. Gravity is cosmic bombardment. So why did it fail so spectacularly?
Well, the fatal flaw, as scientists like Maxwell and Poincaré later showed, was heat.
Heat.
For the push gravity to work, the collisions had to be inelastic. They had to lose energy. And if matter is constantly being bombarded by high-energy particles in inelastic collisions,
All that energy has to go somewhere.
it transfers as heat. And the calculations show that matter would just vaporize almost instantly.
So the universe would burn up. But even before the heat problem, there was a speed issue, right? Identified by Pierre-Simon Laplace.
That's right. Based on observations of the moon's orbit, Laplace calculated that if gravity were transmitted by particles, its speed would have to be at least 100 millions of times greater than that of light.
So basically instantaneous.
Instantaneous transmission. It was the only way classical physics could save itself from action at a distance, but physically it was absurd. It took Einstein to finally turn that whole assumption upside down.
And say that nothing, not even gravity, can move faster than light.
Exactly.
And that leads us right into the 20th century, which didn't resolve the particle versus field tension. It just codified the conflict.
That's a great way to put it. Einstein gives us the ultimate continuous field, and quantum mechanics gives us the ultimate discrete particle.
His 1905 Annus Mirabilis, special relativity, photoelectric effect, E equals mc squared.
Showing us that mass and energy are just interchangeable forms of the same stuff. Then, in 1915, general relativity sealed the deal on the field view. Gravity isn't a force, it's the geometry of space-time itself, warping.
Continuous, smooth, dynamic.
Meanwhile, the quantum revolution was confirming the absolute reality of discrete chunks. But just the electrons.
The very definition of a fundamental discrete particle.
It's the carrier of the negative elementary charge. It's incredibly lightweight. And its arrangement in orbitals, the valence electrons, that determines all of chemistry. It's a countable, discrete piece of matter.
So you have general relativity describing a smooth, continuous gravitational field, and quantum mechanics describing a lumpy, discrete existence for everything else. And reconciling those two is, well, it's the central crisis of modern physics.
It is. But this tension also led to astonishing breakthroughs. I mean, think of Paul Dirac. His 1928 equation tried to reconcile special relativity and quantum mechanics.
Huge hurdle at the time.
Huge. And he found that the math required a solution for particles existing in negative energy states.
Negative energy states, what does that even mean?
It sounded bizarre. Dirac's interpretation was the concept of the Dirac sea. He hypothesized that the vacuum was actually filled with an infinite sea of these negative energy electrons.
So they're undetectable.
Until an empty state, a hole, was created in that sea. And that hole would behave exactly like a positive charged electron.
Which is how he predicted the positron, the electron's antiparticle.
Predicted purely from the math. And it was confirmed just 4 years later.
It's amazing. And this tension played out in some very dramatic, very personal debates, too.
You're thinking of Eddington and his student, Chandrasekhar.
Famous dispute, yeah.
Eddington was foundational in understanding stars, showing they behaved as ideal gases. He was a champion of the classical smooth stellar model.
But his students' math told a different story.
Chandrasekhar derived the mathematical mass limit for stars, the Chandrasekhar limit. It proved that a star above a certain mass, once it burns out, must collapse into a completely unknown, incredibly dense state.
And Eddington just refused to believe it.
It was a shocking moment of scientific hubris. He clung to the idea of a smooth, predictable universe. He famously suggested there must be some law of nature to prevent a star from behaving as the pure math dictated.
He was wrong.
Completely wrong. And that dispute, that refusal to accept the math, it presaged the discovery of neutron stars and eventually black holes.
Which sets the stage perfectly for the modern era, where physics kind of cycles back to try and use these ancient ideas of self-similarity and scale to bridge the divide.
We go straight back to Leibniz. His ideas on self-similarity were formalized by Benoit and Mandelbrot in fractal geometry. And today, some theoretical frameworks propose an ultimate organization based on scale, what's called the infinite hierarchical nesting of matter, or IHN.
Okay, so what does IHN claim about the discrete parts of the universe?
IHN suggests that objects, for the meta-galaxy down to stars to nucleons, are grouped into a discrete number of matter levels, maybe 13 distinct tiers.
And properties repeat.
That's the remarkable part. Properties periodically repeat across these levels with an enormous ratio of sizes, about 10 to the power of 22. So a structure at one scale is analogous to a structure 10 to the 22 times larger or smaller.
It's like a set of Russian dolls where the rules repeat at every scale. But how does this framework integrate with fields like gravity and electromagnetism?
Well, IHN informs a specific, and I should say highly theoretical interpretation called the electrogravitational vacuum model. It tries to revive the spirit of Lesage's mechanical explanation, but in a relativistic context.
It posits that space is filled with moving particles.
Yes, two types. Relativistic gravitons, the smallest particles for gravity, and treons, the smallest charged particles.
Wait, if the vacuum is filled with particles, doesn't that violate special relativity? Doesn't that create a preferred reference frame for the consider problem?
That's the crucial challenge. The model tries to address it by saying their effect is a dynamic medium created by their fluxes. There's no single preferred frame for the whole universe, just a local frame defined by the particle fluxes around you.
So the relativistic effects like length contraction and time dilation are caused by moving through this local medium.
That's the idea. It aligns with the results of special relativity without needing an absolute empty vacuum.
And this model goes even further, suggesting the strong nuclear force is just gravity on a different scale.
That's the most compelling and maybe most controversial part. It suggests the strong interaction at the nucleon level is actually a consequence of strong gravitation, with its own gravitational constant, acting at that tiny scale.
A unification based on scale.
Yes.
And to make this tangible, the sources even describe a hypothetical application, an engine that uses this vacuum energy.
They do. Based on the idea that the preons are charged particles, you could theorize an engine that uses a cone-shaped chamber with powerful electric and magnetic fields.
To harness the flow of these preons in the vacuum.
Exactly. The fields would manipulate the charged preons passing through, deflecting them, transferring momentum to the cone walls, and generating thrust without fuel.
And they calculate a potential thrust.
A minimum thrust force of 724 newtons. It's a theoretical, physical manifestation of this whole theory of a nested, particle-filled reality.
So, what does this all mean? We've traced this incredible journey. We started with Democritus's hard atoms, moved through Newton's particles versus Leibniz's continuous monads, up to Einstein's continuous field and quantum mechanics' discrete particles.
And today we see theories like the infinite hierarchical nesting model trying a profound synthesis, that the universe is both continuous through its scaling similarity and discrete through its particle-filled levels. The modern approach isn't solving the tension, it's defining it relativistically.
To leave you with a final thought, let's go back to philosophy. Consider Immanuel Kant's four antinomies of reason. Kant showed that human reason seems equally capable of proving two contradictory claims.
And one of those antinomies is exactly our question, whether matter is infinitely divisible or whether it stops at a fundamental piece.
We started this deep dive exploring matter's finite, discrete nature, and we ended with theories proposing infinite nesting and continuous dynamic mediums.
So what if the persistence of this tension between discrete particles and continuous fields isn't a failure of physics, but a fundamental limit of human reason as we try to grasp the thing itself? Is the structure of reality just designed in a way that will always defy a single definitive answer?